probability is
1 by 2.
1 by 2.
Yes, yes.
So if you measure one of the qubits, then you are sure about
Other
remaining.
remaining bits.
Okay.
Yes, sir. One more question, sir. How do we achieve this entanglement?
Yes. So I will address that question. Second question I am asked.
Okay, sir.
I will address. So in a quantum computer or lab scenario, we can create this kind of circuits, quantum circuits. So these qubits are initially 0, 0, and we apply the Raman gate and then the control not gate we apply, and we can see that here this amplitude is 1 by root 2, 1 by root 2. Okay, that is 0.707. See here, this is the amplitude, that will be 0.707, and probability of measuring 0, 0 and 1, 1 is 1 by 2, 1 by 2. Okay, but when we measure a qubit, we do not measure amplitudes, we measure the probabilities. Okay, what we do is this process of this qubits are in superposition, so these things are probabilistic. So you do not know in one results. You do the several iteration of the experiment, and let's suppose here if you say that this experiment we are running, so we are not running in one time. If you run in one time, then what will happen? You will get either 0, 0 or 1, 1. So if you get 0, 0, then what you will say? That my qubits are 0, 0. But this is not true. If you run the experiment several times, let's suppose 1000 times, then what will happen? Almost 50% time you will get 0, 0, maybe around 500 times, and similar 500 times you will get 1. So to get this probability distribution, you need to run the experiment several times. If you run it one time, then you will not get the true picture of this quantum circuits.
In general, how many iterations are performed?
Generally 1000 to 8000 is the requirement.
1000 to
8000. 819. So is this thing clear now, or any doubt is there? Because we have spent so much time on it, and it should be clear to everyone.
So there are only two states, 0, 0, 0 and 1, 1, 1.
Yeah.
There are 3 bits and there are
3 qubits. Okay, 3 qubits we want to discuss. This example.
yes, 1 by 2 probability.
This one.
Yes.
So in the 3 qubits there will be
Other one is 0, 0, 0,
Yeah.
0, 1, 0.
all will remain, all will have amplitude 0, and their probability will be 0. So out of those 8, we are having this 2 only. So we can construct this kind of quantum circuit which can give us this kind of states. Like in case of 0, 0 and 1, 1, we can have this kind of circuit. So we can have in this kind of scenario, we have a third qubit, and we can apply the CMOS gate, and then we have this kind of states. So it's possible and easily doable. So far so good. Any this thing is clear, or So now we are ready with these 2 quantum phenomena which are very important for quantum computer, and which are basically this quantum computer is based upon. Now can anyone tell what is this quantum parallelism? If you understand superposition very well, then you will be able to tell. What is this quantum parallelism? Anyone mind guess? Anyone by seeing the diagram also you can try. Large. Yes.
I will try the theory.
Yes.
Replicating what we could call a large scale on a small scale. With more information.
Anyone else want to try?
Simultaneous
Yes.
of multiple bits of multiple data.
Multiple qubits. Multiple qubits. Yeah. So that's good. Yeah. So basically, what we are saying is, in case of this normal or classical computers, what happens? If you want to compute some function f, suppose, if I ask you to compute some function f on value 1, 1, 0, so maybe let's call it this thing. So what you will do is, you will have a function implementation in C or some programming language, and then you will pass this parameter, that is this 4-bit value, and it will compute it. It will give you the answer. Okay? Perfect. If I ask you to compute again for maybe 1001, then what you will do? Again you will call this function. So basically, if I ask you to compute for all possible 4-bit values, then what you will do? In series, one by one sequentially you will apply all zeros to all ones, that is 2 power 4 combinations. maybe like this. Okay, and you will be applying F on them. So it's basically, if you see this, classical computers are sequential in nature. Okay, so suppose this instead of this 4 bits, suppose we are having 30 bits function which take a 30-bit input. Then classically what will happen? We will have this 2 or 30 states and we will apply one by one. So what are the current ways to do it fast in classical computers? For loops, yeah, parallel, not out. So we can, yeah, please. Multiprocessors, yes. So what we will do is, this is space, let's suppose it is 2 power 30. So we can divide this space and give it to separate CPUs and we can do it parallel. So suppose you have 100 CPUs, so what you can do is, you can divide it into chunks of 100 state space. But you have 100 CPUs, no? You have some limitation. So if I increase this space from 30 to, let's suppose, 2 power 100, what will happen? This will be a very large space, and for 100 CPUs, what will be like? 100 CPUs means 2 power 7 I can divide it. So we assume you have 128 CPUs, so it will be what? 2 power 7. So the state space will be like this, 2 power 93. So 2 power 93 computations each CPU need to process if we have 128 CPUs, and that's a very large space, not visible on current CPUs. So by default we are doing this parallelism, but it is not parallelism. We are employing more resources. We are not doing parallel processing. We are basically having more CPUs or hardware and trying to do it, but at this kind of scale, the technique will not work. So Sorry, which processor? Yeah, so we can increase the processor, na? 100, so you can make it 400 or maybe 4000. But at this scale, so let's suppose you have 10,000 processors or maybe 1000. So it will be around 2 power 13 or so. Just divide this by. So I want to do it computation for 2 power 100. So 30 you divide and it will be remain 87 here. So still this 87 is very large. Maybe you can put it as a 1 million or 1 billion also. Then also it will be 2 power 30, 1 billion processor if you put. Then it will be 2 power 30 and it will be again 2 power 70. So 2 power 70 speed is a very large scale. That is not visible on current CPUs. So here what I want to say is that in classical we are basically just doing kind of sequential or serially we will be doing this thing if I want to compute this F on all possible states. But in case of quantum computer, what will happen? Can anyone tell?
It does it parallelly at the same time, right? So
Yes. So what will happen in the quantum computer? We will have, instead of this 4 bits, what we will have? 4 qubits. Okay, so let's call it this 5-4 qubit system. And if we create equal superposition of them, then what we will get? Can you tell? We'll have superposition of up to what? So that we can create easily. 4 qubits are there. If we apply 4 Hadamard's on them, then we will have this kind of superposition states. Now, if I ask you to apply the function A on this 4 qubit state, then in turn what will happen in the quantum system or the quantum computer is F will be applied on all of them in one application of this F on 5-4. So we are applying F on this 5-4 qubits with the quantum gates we can implement it, and by applying this F on 5-4 or 4 qubit state, in turn in the quantum computer it is being applied on 2 power 4 states simultaneously. In one go, this computation will be performed on a quantum computer for all possible different values. And this is the thing which is called quantum parallelism. Maybe if we have 100 qubits, then what can happen? So we can have 100 qubit system and we can create superposition of them, and that way we can apply that. While this thing was next to impossible in classical because of the large state space, but in case of quantum it's pretty easy. With only 100 qubits compared to bits, you can have 100 qubits and you can do it. But there is a catch. What is that catch? This app has been computed on all of them, but we will not have access to all the computed values. On measurement, what we get? One of them. Okay, so maybe you can get f of 0001 on measurement. Okay, so this is the catch here. Maybe in the quantum system, we will be having all states and we are able to compute f on all of them, but on measurement we will get the one result. So here comes the quantum algorithms. So what this quantum algorithm does is, this app is computed on all of them, but we are interested in certain app or some solution or some answer to our problem that we are interested. Suppose we are interested in this app of 000. So in the quantum algorithm, what they do is they do some tricks or some kind of elegant things which increase the probability of this f of 000. Because all of are having some certain probabilities, no? So what that does is, that quantum algorithm does is, the desired answer or the solution to our problems, they increase the probability of those states and decrease the others. So if you increase the probability of one certain state, then it will automatically decrease others. Right? We don't know solution, but what we are doing is we are creating a general algorithm. What it will do is, whatever the please focus. Yeah. What I am saying is that we do not know solution. Okay. So suppose this is x1, x2 dash, x1, x2 dash, and x3. So this is our f. Okay. And if I implement this f and I write some program, so I do not know the solution. What I do is I implemented this f, and my program will give me the answer depending upon the f. So in this case, what will be satisfying assignment for this function? If I ask you what values of x1, x2 and x3, I will get 1. These are primary variables x1, x2, x3. So in this case, the solution is no, 1, 0, 1. x1 should be 1, x2 should be 0, so complement will be 1, and x3 should be 1, and their ending will be 1. So here you do not know the solution in advance. What you did is you write an algorithm, whatever function f you give, it will give you the answer to it. So same way in quantum, whatever the solution that needs to come out of that algorithm, it will increase that solution's probability. And there is a constant that this probability is sum will be 1. So if you increase certain state's probability, then it will decrease the others. So this thing will be 1. So after that algorithm, we will have with higher probability getting of this thing and very less probability of getting other states. Okay. So there are, let's suppose there are 16 states. So solution state is this one. So maybe a 90 or 80% time will get this thing, and the remaining 20 times, the remaining 20% you will get other states. So if you do the experiment several times, then you will have a probability distribution, and if we are getting something with more than 50% probability, we are sure that this is our answer. So far clear or without?
So sir, meaning is that
Yes, please.
in quantum algorithm, whatever we are writing in quantum algorithm, that is basically dependent upon what we want at the output.
Yeah.
For example, I want 1010 state, right?
Yes.
So I have to write my quantum algorithm in such a way that so many input states are there. This algorithm will give me output as 1010 with highest probability.
Yes.
Right? Because we are interested in that output.
Yes.
And other outputs, other states will be having less probability.
Yes.
That means for all the states we will be having different quantum algorithms?
No.
Then
So
one
it depends.
algorithm will
No,
go
no.
for all the states?
No, no. Its problem is specific. If you are doing for searching, then there will be certain algorithm. If you are doing some period parting thing, then there will be a different algorithm. Like in classical also, no? You have a sorting algorithm. For that, you have some algorithm steps. For searching, you will have different steps. And maybe for some other problems, you will have different algorithms to do the thing.
Yeah,
But in case
you
of-
are telling that
yeah.
we are interested in this particular output.
Yes.
You have to write the algorithm like for that.
Yes,
Out,
but-
for example, 3 qubit state, we are having 8 possible outcomes, and out of that only I am interested in one.
Yes.
So for whatever operation I am performing here, after that we are having so many we are having output of superposition of these.
Yes.
We are interested only in one. So
Yeah.
after that, this quantum algorithm will give me only that output. That I want to say that
Yeah.
this should give me the algorithm should give me that particular output, and that is dependent upon in which I am interested.
Yes. So
So-
in which is the thing that we are interested in this finding satisfying assignment of this step.
But
That is
sir,
our problem.
In cases of problem statement dealing with uncertainty, you don't even know what is the output.
Yeah, but
So we
certain-
don't know
How
output in
we
advance.
Uh,
We don't know output in advance.
no, you don't know at advance. What I am telling you is
So,
that
but at initial stage,
yeah. One more we can take the questions. Yeah.
So at initial stage, you were talking about alpha and beta. During that time, you said that when we are setting alpha mod, that time you can set the probability. If you want that probability should be 0, so you can set alpha as mod. So that will get the probability as mean. And also that alpha square, if we confirm that the probability of getting 0 is confirmed. So that can be taken.
No, actually what we are trying to say here is that in case of that concept is that this mode alpha and this alpha are amplitude and the probability. But suppose if we have a superposition of 4 qubits, then we will have 4 states and we are searching for one of them. In this case, if I say that what we are looking for is that this is given f and this is x1, x2 dash and x3. So here we are looking for a solution of this satisfiability problem. We do not know the solution in advance. Okay, so what we are doing in our algorithm, that we will have superposition in the beginning. So if we have an equal superposition, then what will be there? We will on measurement we will have all the states with same probability. So you cannot distinguish your answer. No? If you create equal superposition like this, yeah, here. So if we have all of what, yeah, so we can create this kind of equal superposition where this 3 qubits states on measurement will have same probability on measurement. But I am interested in one of them, that is 101. And I am not interested in 101. I am interested in finding solution of this f. And what is the solution? We do not know in advance. So what we are interested in? We are interested in finding solution of this f, that is x1, x2 dash, x3. So equal superposition can create by applying Hadamard gates, 3 Hadamard gates, and it will be having this kind of states. But if you measure them, what will happen? You will have this 101 and 00 and all states with same probability, that is 12.5. Or that's basically 1 by 8. So you cannot distinguish your answer with other non-answer values. So for that, what you have to do is you have to update or change this y3 in such a way that for your function, whatever the solution. So in this case, this is the solution. It should increase its amplitude and turn its probability. Okay. So what will happen if you increase its probability or amplitude? Then others' probability will automatically decrease. If I make this its probability 80%, then other 7 states will have combined 20% probability. And if you measure this circuit, then 80% time you will get 100. That could be your answer.
Is it
In that
21?
case, I want to say that I am interested in 101.
Yes.
So I have to design my quantum circuit
No,
in such a way.
I am not interested in 101. I am interested in this function solution. This function can be anything. This
But
function
how we are increasing the probability of 101?
that we will see in the second presentation, where I will show this thing. using Rover's search
So that
algorithm.
means
we can-
solution of x1 is to x3 is 101 because it is giving highest probability. It is like that.
Yes.
So in general, what we want to say that thing is that quantum circuit, how we are designing that logic, I wanted to understand.
Yeah, that I will cover in the second
Next
session.
session. Okay, no problem.
So, trying to understand whatever your F is, you can get solution from it.
Is it related to Hopfield network?
Sorry?
Hopfield network that we are having associated with it. Is it related to that?
No.
Because there also we are trying to match the
Yeah.
nearest.
So here we will be doing this Rover's search algorithm that I will explain the second session on this. That time when your queries will be answered or maybe we will re-ask again that time. Other query was there somewhere with you? Yeah, please. So if you are getting confused, then it's okay, you are learning. The quantum mechanics or quantum physics, it is said by Richard Feynman, a great scientist, that if you are saying that I am not getting quantum mechanics at first time, then you are getting it.
And can we have your fuzzy sets also like membership value?
No, not like that. It's not related here.
No, in terms of probability, I can have a possibility. Can we
Yes.
have such kind of scenarios where we are not able to measure the probability?
No, like that here in the we are in quantum domain and superposition, and the thing is that we just can measure those qubits. Okay, and on measurement we can get this kind of answer with certain problems.
Yeah, but when we do the experimental study, experimental results, then we get the probability value.
Yes, so what we do is we run the circuit several times to get that probability distribution.
When
Now
we
that-
are not having experimental results, or it is something like when we are having uncertainty.
Yes.
And with respect to the knowledge base that we are having, we can, that's the way the fuzzy logic can be pictured.
Yes, but I think I am not able to connect your thing into this thing.
Sir,
Yeah.
I know what is my expected output.
Yeah, means basically we know the solution to our problem.
Yes.
We can check it by plugging it into the function.
What if for applications where we don't know the solution?
No, solution you do not know, that's okay. So you get some solution or approximate solution.
How do you calculate that?
Yeah. So if I say that, okay, I am doing for this traveling salesman problem, okay. So you do not know what is the optimal solution. So maybe I can give you some solution, okay. And I ask you, I say, okay, this is your approximate solution. You can check it. So what you can do is, how you can counter this thing. You will try a simple solution, and if you get solution better than mine, then you will say, okay, sir, your result is wrong. I get a better solution. And if on your trials you are not able to give me a better solution than the which I provided using quantum, then you will say, okay, this is approximate or the best solution available. So the idea is that you have some solution or a solution and you can cross check. Or if you find better solution, then you can say, okay, this is the better solution. But in case of this, if you are saying that we are getting approximate solution, then you will not find very better than this approximate solution. Or maybe you can try for small instances, like don't go for large and traveling salesman problem. Go for 3 or 5 kind of things, and 3, 4, 5 you can compute it yourself manually, and you can check your results with the quantum output also. So in that case, you will know that if 5 cities are there, and I can do it on paper also, and I can check the solutions, okay, and quantum will give some answer.
Apply it for higher groups.
Then if it is working for 5, it is working for 10, then we expect that it will work for higher also. So yeah.
So, for example, for example, machine learning also provides analysis to persons.
Yes.
It's an answer to persons, but we don't know what the looking for. It would be fair to say if we ran, say, searching algorithm, we use
Yes.
that one and we run it for an 800 iterations, 8,000 iterations. Then it would be fair to say the state that we get the highest probability for would be the answer.
Yes. Shall we move next, right? So far this quantum parallelism is clear. These two phenomena, superposition and entanglement, and then this quantum parallelism is clear, then majority lesson we have already learned for this quantum computing thing. So case here is that? Yeah.
Like we are doing parallelism for this all 4 bits at a time.
Yes.
Right? But we are not doing any kind of parallelism for individual bit 0, 0, 0. So that parallelism is not there, only for 4 bits at a time.
No. All possible states with 4 bits. What are those?
60.
16. So we are doing for 16. In one row, one quantum number. In case of classical, we do it one by one. Classical, you will do it one by one for all possible 4-bit values, and there will be 16 units. But in case of quantum, using qubits and superposition, it will be done in 1 minute.
Sir, in sequential, I am giving 16 times inputs, right? And then I am getting corresponding outputs. While in quantum, I am not giving any input, actually 4-bit. So all for 16 states are simultaneously operated, and then I am measuring, right? But since I have to find the probability for the same thing, I have to perform 1000 times, or as you said, 8000 times, then I will be able to get the distribution. So which one is better? Classical is better because only 16 operations we have to perform. 16 times we have to perform.
So as Bankal said, this thing we are explaining with very small n example, but
Okay.
actual problem occurs with large n. So suppose your n is 100.
But again, there also we will have to
No,
perform
in that case
8,000, 10,000 operations, right?
Sorry?
In order to get the distribution.
No.
Stuck here.
No, 1000 equation is sufficient. In case of larger n, so doesn't this thing that x will remain same for second session also. Whatever I am showing here is with a small example of 3 or 4, but this concept is equally valid for larger n, such as n is equal to 100 or 120 or so. In this 3 or 5 you will say, okay, I can do it on classical computer also. So this 16 is not a big number here. I can do it in microseconds on a classical computer. But the idea here is that this parallelism gives us advantage for larger n's.
And that's
So,
right, sir.
100 is there.
Larger end, but again we have to find the distribution, right?
No, ma'am. For distribution, what we are saying is that if we do 1000 iteration or 8000 iteration of that, then in that distribution itself, you will get the answer with 80% or more. So for that, you need not run for 2 power 80 or so iteration for probability distribution. The iteration or the shorts we call remains 1000 to 8000. So we will see the global search, then you will be able to appreciate the thing which we are discussing now.
Sir, one question, sir.
Yes,
Sir,
please.
in normal computer, parallelism can be achieved using pipeline also.
Sorry?
Using pipeline technique in normal computer.
Yes.
So even if you don't use the multi-core or multi-processor, pipeline can be used.
Yeah.
So here, no such pipeline, only a number of bits.
Yeah. So in case of pipelining, what happens? There are certain steps in our computation,
Yeah.
maybe 4 or 5.
Yes, sir.
Like those many steps are there, or maybe more.
Yeah, perfect.
So you can have a speed of 6 more times, or maybe 8 times more speed of get. So what will happen in that case? So as I told, if suppose we are trying for 2 power 100 kind of space, and suppose you have 1 billion processors, that 2 power 30 processors you have, and you are saying that I can do pipelining, so I am assuming that 8 times of speed up can get. Maybe 8 steps are there and you are executing them in parallel. So 8 is plus what basically? 2 power 3 only. So I can divide by 2 power 3 also. Still it remains very high. Understand this thing? It will be again 2 power 70 or so. So maybe whatever classical things you can try, pipelining or multi-core, multi-CPU or HPC, whatever you try for large n. So I am looking for only 100. If I put it as a 200 or so, then whatever parallelism you will do, it will not solve the actual problem. Got that thing?
Thank you.
Sorry?
When they say we are measuring.
Yes. Yes.
We are writing an algorithm.
No. In a quantum computer, you have these operations built in. So what they do is, suppose we encoded our information in electron. Suppose electron has a qubit, and we have said that this ground state is 0 and excited state is 1. Okay. Then what we will be doing is, there will be some physical devices which will measure this energy levels. And on measurement, maybe in superposition, this electron can be in between. On measurement, it will be at the ground or certain state it will be found. So there will be some physical devices which will be doing, and it will tell you we got 0. So you do not worry about that. We have this quantum qubits we are having, this phenomena we understood, and we should have this quantum gates. Okay. So understand this quantum gates. As you know that state qubit is in some states. Let's suppose this is state 5, and if I apply some quantum gate here, okay, then what it will do is it will change the qubit state to 5'. In case of quantum, for every quantum operation or quantum gate, there will be an inverse. Okay. In case of classical, it is not true, but in case of quantum, for every quantum gate, there is a reverse quantum gate possible, and that is nothing but that is called U-level, or it is called transpose conjugate. So these gates can be written as a matrices. These quantum gates can be represented as a matrix, and qubit state also can be represented as a matrix. So let's do some thing. Suppose this is my qubit. Okay, so I can write this qubit 5 as a column vector like this. Understand this thing? So whatever the coefficients or these attributes are there, we will write as a column. For single qubit, it will be 2 cross 1. For 4 qubit, it will be 2 power 4 cross 1. So, okay. So like this. So how we will write this is state 5'3", 5'3" as a what I am trying to say here is that every qubit state can be represented mathematically as a column vector, and in that column what we need to write is the coefficients of basis states. So in case of 3 qubits, there will be this 8 basis states from 000 to 111, and we will not be writing these states, we will be writing the coefficients alpha 0, alpha 1, alpha 0. So this will give the information about this Python qubit, and we know that the first thing is coefficient of this state 00, and last one is for 111. In case of this gates, this U for if you talk about single qubit, then it will be a matrix of 2 cross 2. Okay. So here I can write like this: 2 power n cross 1. So this n qubits can be written by 2 power n cross 1 column, right? And n qubits gate can be represented by 2 power n cross 2 power n matrix. So in case of 1 qubit gate, what will be happening? It will be a 2 cross 2 matrix. Okay? And this matrix, corresponding to this matrix, there will be a physical operator which will do the desired thing. Okay? So understand here is that this matrix is a square matrix, and the property of this matrix is that its transpose conjugate exists, and that is nothing but U inverse. So suppose for this U, its transpose conjugate is this U star, and that is nothing but U inverse only. So for every quantum gate, there will be a inverse quantum gate exists. Okay? And it will take this into original state. So we apply this gate U on this 5 state, we get 5', and we apply U inverse on this 5', and we will get original state 5. If you remember from the classical one, if you apply an AND gate on 2 bits, then what you will get? For 0 0 you will get 0, 0 1 also get 0, and for 0 1 1 0 also get 0. Only for case of 1 1 you get 1. But if I give you an answer that I got 0 on ending 2 bits, can you tell me more what were the bits? Or from the output, can you go to the input? This is output, suppose 0, and these are A and B classical bits. So what I am asking is that I have output of 0, and I apply AND gate, and I am asking you what is the A and B, the inputs here. So you cannot tell with 100% that it is 0 0 or 1 0. So it means it's not reversible. But in case of quantum, from the output you can go to input also. Okay, and so these quantum gates are reversible. Do we have any classical gate which is reversible? Classical gate that is reversible. Sorry? Not gate, yes. So not gate, then if I get 0 then I can tell that pass 1. So only the not is reversible thing in classical, rest the gates were irreversible. Okay. So you know this thing that there is A and B are having some energies or in classical some volts, and you combine them to get some 1 bit output. So basically 1 bit of energy we are losing in between. If you apply this AND gate, then what will happen? So 1 bit of energy will be dissipated in the environment. But in case of quantum, this energy will not dissipate. Why? Because you will have same number of input bits or qubits, and you will have same number of output qubits also. So, and the information will remain here. You can go from forward to backward or backward to forward directions. So in this case, this quantum system reserves energy also, okay, to classical ones. And if you see that in classical chips, we say that these chips are heating or they're compacted, and because of this thermal emission, when we measure this kind of bits, and 1 bit of energy is dissipated. But in case of quantum, this will not happen. So far so good? Yeah. These are the quantum gates summary here, and so as I told that this Hadamard gate, and this is the corresponding matrix. Okay, so this is a matrix, and as I already told that if you have suppose we have this state. Only 0. So this 1 times 0 plus 0 times plus. So here you have a state like this. 1 times 0 plus 0 times 1. So what is this state basically? Can anyone tell? It is 0 only. So I can write it like a matrix also. What I will be writing in this matrix? Can anyone tell? 1 0, coefficients of 0 and then 1. Perfect. And I am saying that this is the matrix from Hadamard gate. So what I need to do is just multiply these two matrices. So this is my state, and 2 1 0 is my this 0 qubit, and I am applying Hadamard. So as we previously seen that we are trying to apply Hadamard on this 0 state, and what we told earlier is that it will give us superposition. So just multiply these two matrices, okay, and what you will get? You get this thing. Okay, what you will get? To multiply these two matrices, that will be basically Hadamard applied on 0, and you will get this kind of matrix. And this is nothing but what? It is, if you represent it as a quantum state, then this 1 by root 2 is the coefficient of 0 state, and this 1 by root 2 is coefficient of 1 state. That is nothing but this kind of state only. As I told earlier that, so what we are saying is that this just matrix multiplication is there, and if you apply some gate on some qubit, then you will get another qubit. Okay, that is this one, single qubit only, and it is have two coefficients alpha and beta. But the beauty here is that originally we have only 0 state, now we are having superposition. Okay, and it is nothing but a rotation on that block sphere. If you remember, the block sphere, see, suppose 0 is here. So what I did is, somehow I need to make it, keep it here. So this state x is basically nothing but 0 plus 1 by root 2. This plus x is the sequence superposition state of 0 and 1. And if I say that I want to apply Hadamard on 0, then what I will be getting is this. So it is nothing but just to change this theta and phi, or just do some rotation on this block sphere. So every single qubit is a kind of rotation on this block sphere around this x, y, z axis. Is it okay? So, okay, another important thing that is called control node gate. So as it is 2 qubit gate, you are already aware, and it will be applied on 2 qubits. 1 qubit will be control and other will be target qubit. Okay, and as I already told that for 2 qubit, the matrix will be of what size? 2 power n close to power n. That is basically 2 power 2 close to power n. That is 4 plus 2. So this kind of matrix is there, and the property of this matrix is that. Okay, so since this is a 2 qubit gate, so it will be applied on what? It will be applied on the state of 2 qubits. Okay, and 2 qubits have 4 coefficients. So those will be what? Alpha 0, alpha 1, alpha 2 and alpha 3. And if you multiply them, then what you will get? Alpha 0 dash, alpha 1 dash, and alpha 2 dash, and alpha 3 dash. Okay, and property of this CMOD gate is that if you apply it 2 times, then you will get the original. But it's self-inverse. Not transversal gate, it is self-inverse. Same way this ATAL is also self-inverse. And we call them as a Hermitian operator also. FOL is nothing but these 2 qubits are control qubits. If they both of them are 1, then only it will change the target qubit current. But using this Toffoli gate, you can implement AND and NOT gate. And as you know classically, if we have an AND and NOT gate, then what we can do? We can implement NAND or we can implement all possible classical universal gate kind of thing. If you have a NAND gate with us, then we can do universal all operations in classical. So using this single Toffoli, we can use it as a AND gate also, and we can use it as a NOT also. And if you have these 2 gates, then you can have all combinations for classical Toffoli. So for classical, this Toffoli is sufficient. To do all classical things, Toffoli is sufficient. But as we have seen here, there are other gates also possible. Those are some rotation. This Z is a rotation gate, and this Alamard is giving us superposition. So these gates are giving us this superposition and this entanglement phenomena, and gates are making it faster. Okay. So classical, everything can be done with this gate only. The other gates gives us other things which are not there in classical. Suppose this Z gate is nothing but rotation around Z axis by 180 degree, and it is rotation around Z axis by theta degree, and corresponding matrix is this. NOT gate is basically our classical NOT, but it is more than that, and corresponding matrix is this. And if you apply this thing 2 times, then you will get the original. And this NOT is nothing but it is X gate, and it is rotation around X axis by 180 degree. So if you remember that block square diagram, so what I am saying is that single qubit gate operations can be done by rotations around X, Y, Z axis. So this X gate is nothing but, or NOT gate is nothing but rotation around X axis by 180 degree. So our concern is that we have this kind of gate with us, we have the qubit with us, we are not worried about what is underlying hardware that is implementing these qubits, or we are not worried about how these quantum gates are being implemented. So if you think of these gates, they are basically some microwave pulses are thrown on these electrons at certain frequencies. They do these kind of rotations, and those rotations at a specific angles around specific axis is our gates. So when someone asks, maybe I think you asked that how you are going to implement these gates, or basically how you will create the entanglement. So entanglement is nothing but just a Raman gate and control NOT gate. So we can implement this control NOT and this Raman gate by throwing micro pulses on electron at certain frequencies, then it will do the Raman and it will do the control NOT. And these are nothing but just rotation for those axes. So that will be that. So gates are clear, okay, and one is a quantum circuit. In classical also we have this kind of circuits, and gates and NOT gates and some bits are there, and we get some answers. So likewise in quantum also we have qubits. Okay, these are our qubits, Q0, Q1, Q2 are qubits. We have some initializations, like we are beginning with zeros or some particular state, some particular qubit and some particular state we want to keep there. Generally classical what happens, we initialize with zeros all the variables also. So likewise, some initialization replace that, and then this quantum gates which do the our meaningful computation. Whatever algorithm like shows or clovers or other algorithm which we have to implement, we can do it using quantum gates. And then finally we measure them. So on measurement we will get the answer with certain probabilities. What we do is we run this several times to get the probability distribution and get the answer with high probability on measurement. And here also we have some classical bits also with us. Those are represented by these double lines, and depending upon their value, like if it is 0 or 1, we want to do some gates we want to apply on this qubit. So what you want to do is, if this CRX qubit is 1, then we want to apply X gate on this second qubit Q2, and if this CR gate is 1, then we want to apply Z gates. So whenever these bits are 1, these gates will be applied on the qubit 2, basically conditional gates. Okay, and when it depends on the classical bits. Here this C0 is what? It is control qubit, and it will be applied in this qubit 1 is 1, then it will be applied on the target qubit setting. So the difference is very obvious, this classical and quantum circuits. As I already told that we have this qubits in the quantum circuits, and these gates are reversible, and we also have universal quantum gate set here. Those consist of C0, delta mod, and the X gates governed by quantum mechanics. Why? Because in quantum mechanics we have these phenomena like superposition and entanglement. These are governed by classical physics. Irreversible except not gate case, and it's reversible for every gate. So since gates are reversible, then entire circuit that will be also reversible. If you apply those gates in reversible, then you can get to the original state. And there are these different technologies to implement them. So in case of quantum gates or qubits, superconducting is the most promising, on which all leading companies like IBM and Google are working on to have a quantum computer based on superconducting technologies. Quantum computing architecture is compared to classical ones, it looks similar to that one. But so see here, at the base or the hardware layer, you will have this physical quantum processor. Okay? Okay? In that you will be having this qubits and these gates and how to apply those gates. So those hardware is there. And there are these microwave pulses to control those qubits or apply the gates. And there are some readouts basically to get the measurement results. These qubits, these things are physical, this thing, and there are this quantum error correction there also, which do some kind of error corrections to the qubits. So this thing is physical, and from developer point of view or the computer science point of view, we are not worried about how these qubits are implemented or how these qubits are applied to these quantum gates. We are on this logical layer, where we have this logical processor with us, which has some good qubits and some gates. And depending upon our requirement, we can take the qubits, we can apply the quantum circuit with our algorithms and take the measurements. On top of that, which is the most important thing, that is quantum algorithms. Maybe hardware is there, everything is there, but if you don't have good quantum algorithms, which gives you speed up compared to classical, then only it will be useful. If you do not have any faster or good quantum algorithms, then this thing is not useful. And what is the property of this good quantum algorithms? They exploit the phenomena of quantum superposition and entanglement. Okay, and there are only few algorithms. Remember this word few, because whatever we can do in classical, we can do it in quantum also. But the thing is that we should have a speed up, and the desired speed up is of exponential factor. Something if it is sitting in 2 power n time in classical, we want to do it in polynomial or linear in quantum. So there are only few algorithms which gives exponential or quadratic speed up. So namely this Grover-Schwarz algorithm and this quantum simulation kind of thing, which gives significant speed up compared to classical. Okay, so it's not like that everything you can do fast on a quantum. So for the research area in this quantum algorithm, which says that we should have the quantum algorithm which exploits this phenomena in such a way that can solve the classical problem faster. And for that, it's not easy to design a quantum algorithm. If you see that this quantum computing is almost 2 or 3 decade old area, but we have only few algorithms which gives us exponential speeds. Okay. Yes, you can implement the quantum algorithms using quantum circuits. Like in case of classical, you have some sorting or searching or quick sort algorithm. That's algorithm. You can implement using classical gates or underlying hardware. So same. Yes. So circuit means you have some instructions. You want to implement something like some operation you want to implement. What happens is the algorithm. So algorithm is like I need some variables. I want to apply some operations on them. So the operation is nothing but quantum gates. So using the quantum gates, you can implement all operations. And initially you need some qubits, you want to create superposition. So whatever we are trying to implement is called a quantum circuit. So in case of classical also, if you go at the hardware layer, some kind of circuit is there, some AND gates or NAND gates are there. And so hypothesis is same here. But the thing here is that we have quantum gates and the qubit gates. Any questions here?
Sir, excuse me, sir.
Yes, please.
Suppose if you want to work a real-time application in the current system, it is not possible.
Sorry?
Suppose if you want to work a real-time application using quantum
Real
applications
Yes,
on
yes.
the classical computer, I think it's not doesn't work.
So you can divide your question into parts. First is that
Suppose if we want to work a real-time quantum application
real-time
using classical computer,
quantum applications
yeah,
using
using classical computers, using this machine, I think it's possible or not?
classical computer you have quantum computer, and what do you want to do now?
The quantum applications,
The quantum, suppose okay, you want to do some kind of searching, quantum search you want to do.
yeah, on classical computer.
So basically you want to, okay, so I got a question. The question is like,
So pure simulation.
can we have a quantum computer environment in classical? Or can we simulate that quantum phenomena and everything in a classical machine? Yes,
Okay.
we
Using
can do it, we
simulators.
can simulate it, but that simulation requires exponential resources. Suppose if you want to simulate 30 qubits, then you will have a state space of 2 power 30. So you need to handle those many states in classical machine. But for quantum computer, it's obvious in superposition. So for 30 qubits, you will have only 30 qubits there in quantum. But if you want to implement or you want to simulate or see the effect and do the same thing in classical, then you will require exponential space, memory, plus exponential computing power also. So for let's suppose if I want to simulate 100 qubits, or you want to do some operation on 100 qubits, then you will require 2 power 100 state space, and you need to operate on them also. But in case of quantum, what will happen? You will have only 100 qubits, and you will apply some quantum gate or some quantum circuit, and it will do the thing. So it is said that even for this 53 qubits, you are not able to simulate what a quantum circuit or a quantum computer can do. Cannot be done on a classical based supercomputer. But one slide will come, it will again address this thing. Any questions? So far this thing is clear. So these are on different layer, different kind of expert parts. Okay. So in this layer, physicists and engineers work, physical layer. In this quantum algorithm, basically this software or this computing guy works. And there are this quantum reflection also, it's also a separate domain. So most of us work on this level, this algorithm level. So what we do is, these quantum computers are made available by IBM and Google on cloud. What you can do is, you will have these gates and qubits there, and graphical interface, and you can program your algorithm using quantum circuits, and you submit that job, and it will be in turn down with quantum computers which they have in their premises, and you will get the results. Okay.
Sir, can you transfer qubits from one place to another place?
Yes.
Via
This
via
quantum teleportation is a phenomena which does this thing.
teleportation.
Yes. So using quantum teleportation, you can transfer a qubit state from one place to a very far away place.
What is teleportation?
Quotation, okay, so we are going out of this thing.
So just
Maybe we can take a question outside.
okay.
Yeah, any more questions here? So this computer, quantum computer is real thing. It's available there. It's not like a theoretical concept. It's available physically there. And one of them is this IBM Q16 Melbourne quantum computer, which is available. And these circles remain. The circles are the qubits basically. So there are 15 qubits. And if you see the things here, single qubit error rate, C naught error rate. So this quantum computer having is 16 qubits, and these gates have certain errors. And there are other parameters, what type of gates are available, okay? And okay, so these things are information about it. So we are focusing on these errors. So, and one more thing is that these qubits can remain in superposition for milliseconds or microseconds only. After that, the states are disturbed. Means maybe you are saying that this is our state in this superposition, but after certain milliseconds or microseconds, this superposition disturbs automatically because of environmental noise and other things. So whatever you want to do in computation, you should be doing in that time window only. Okay, how many gates you can apply on that state, that is limited by this qubit lifetime, that is microseconds or milliseconds only. And second thing is that this quantum gates have errors. Okay, so this gate gives us error, and this error in turn gives erroneous results also on implementation. Some quantum algorithm which we implement, it gives us errors also. So there are these errors, and this qubit lifetime are primary concern for engineers which are trying to implement this quantum computers, because this quantum behavior like superposition and entanglements are exhibited at 0 degree Kelvin temperature. And to maintain that 0 degree Kelvin temperature, if you get some kind of environmental noise, so suppose I am implementing my qubits using electrons, and the outside environment should not interfere with this qubit state. Some kind of vibration or the thermal or radial or what kind of noise is there, error is there. If it is there, then it will disturb the superposition states. So qubits are not resilient to this kind of noises, and that in turn destroys their entanglement, and that limits the qubit lifetime.
Sir, if error is detected, then it simply ignores, because you have had said reverse is possible.
No, ma'am. So you think here that this quantum circuit, if you see here, here we measure these qubits. Suppose we measure these qubits. So what we will get here is 0, 1, 0, something, some classical values we will get. Okay. Now from this classical value we cannot go to quantum state. Before measurement we can go in reverse direction. And as a human being we understand this classical bits. So inside this quantum states we can do reverse. But get the answer, to understand what is the result, we need to measure. And once we measure them, this entire quantum thing is destroyed, we get classical outputs. So see here, and okay, so this thing is there, and you can have access to them, and you can do programming on the quantum computers available on Chrome. These are the breakthrough or milestone quantum algorithms here. So in 1982, Richard Feynman, great scientist, he has proposed this idea of this quantum computer. He said in this way that if you want to simulate quantum mechanical devices, then you should have a computing device which is based on this quantum mechanical phenomenon. So basically he was trying to say that if you want to simulate something which is quantum mechanical, then you should have a quantum computing basically. But that time this thing did not take off. 1982, but in 1992, Joseph has given first quantum algorithm which can find a function whether it is constant or balanced in order of magnitude. While this thing was, suppose if I give you a function, okay, so If I ask you whether this function is constant or balanced, can anyone tell? Constant or balanced? Constant means same output for every input, and balance means half of the time it will get 0, half of the time it will balance. So whether this function is balanced or constant? Yes, please. Is it balanced or not? Sorry? Yes, yes. Yes. Balance. Okay. If I increase some variable more here, still it will be balanced. If I say it is x or xd bar, still it is balanced. So keep it there only. So if I ask you that whether this function is balanced or constant, what you do is you try all possible combinations and then you say okay 2 times like. So there are 4 inputs, you try all of them and you say okay 2 times I get 0, 2 times I get 1, then only you are able to tell it is balanced. So suppose there is some function which say that it is constant. It is like x1 or x1 bar. So it's practically constant only. So, I am taking very small example, but to understand here, this function are example of constant or balanced function. And if I give you a very complex function, which is either balanced or constant, then you require, suppose there are n variables, then you will require 2 power n by 2 triads to find this thing. That is basically exponential in terms of number of variables in this function. Okay, if there are 3 variables, then you will require 2 power 3 by 2 triads. What this Gauss-Joseph quantum algorithm says is that we can do it in one iteration or one implementation of f. Means using quantum gates, you will be implementing this f one time only. And after the results something you get, you can tell that this function is balanced or not. Classically, 2 power n by 2 iteration or computation of this f, but in case of quantum using this algorithm, you can do it in one time. One iteration of f will tell us this thing. So basically, exponential speed up has provided. But this problem is not of very much importance to us. Finding a function whether it's balanced or constant, not very practical applications. So in 1994, Peter Shor gave a quantum algorithm which can factor large numbers, okay, in polynomial time. While classically, the best classical algorithm can factor in exponential. So that factoring large number in polynomial time has variety of applications, and particularly in crypto. You will see. Robots will discuss in detail. Come to quantum simulation. So see here. If we have to simulate something which has n parameters, and if I increase one more parameter, then you need to do it classically, it will take double the time. For n variables, let's suppose 2 power n plus space. If I increase one more variable, then it will be 2 power n plus 1. That will just double the state space which I need to look into it. But in case of quantum, you need to just increase 1 qubit. But while classical, you will need double the memory, double the processing resources. So, quantum simulations using this algorithm can be done easily in a quantum computer. So, that's a very promising application of quantum computer. So, there are these 3 circles of quantum algorithms. Okay, what are those? First is number of qubits. So, as you are aware that this, we don't have large quantum computers with millions of qubits. We have only hundreds or 1,000 qubits quantum computer only. So this qubit is a requirement. We require millions of qubits in a quantum computer. Practical ability means whatever algorithm we are designing, it should have practical applications. Third one is this: it should give quantum advantage. Means something which is not possible on a classical computer can be done using quantum computer easily. So these 3 things are there. And we require something which is common to them. So our interest is in this, where this intersection of these 3 elements, which has a practical ability, which can run in few number of qubits, and which can provide us quantum advantage. So, source algorithm is the example of practical utility because using this we can break RSA and other cryptographic schemes. Quantum advantage is giving why? Because something which will take thousands of years on classical computers can be done in minutes in a quantum computer. But constraint is that we don't have sufficient number of qubits with us as of today. It requires thousands of qubits, but we do not have those qubits. So this thing is there, but we are not into the desired area right now. If we have more qubits or it can run in few qubits, then we will be in the desired area. Google's quantum supremacy. So in 2019, Google with its quantum processor Sycamore, which has 53 qubits, it demonstrated that using these 53 qubits, you can do some kind of circuit simulation and it produces some random sequences. That thing, a circuit is there and produces some random sequences. And the same thing if you want to simulate on a classical supercomputer of that time, that is IBM Summit, they demonstrated, they extrapolated that it will take 10,000 years. 53 qubit quantum computer can do something in 2 minutes, will take 10,000 years for a classical supercomputer. So that is called basically quantum supremacy. We will discuss further into it. But the thing is that it is showing the quantum advantage. Why? Because something is not possible for a classical one, but it can be done easily. Qubits, 53 only, so qubits are also few. But this random generation circuit will generate random numbers or random sequences does not have any practical utility for us. So we are still not in the desired area. So this is a caffeine molecule. Okay, so it is having this kind of atoms, nitrogen, carbon, and this thing. And if you want to simulate it on a classical computer or a supercomputer, we cannot simulate it precisely. We cannot, even a single molecule of coffee, we cannot precisely simulate. Why? Because to simulate it precisely, we have to consider each and every electron, proton, neutron inside the nucleus of this nitrogen atoms. So, and if you want to simulate the effect of this coffee molecule on a brain, then it will become hard. But for quantum computers, for each variable we just require one qubit. Like suppose this carbon is there, let's suppose there are 12 electrons, then we will require 12 qubits to represent this carbon atom. Okay, so with using 100 or 1000 of qubits, you can simulate precisely. But that's not possible for classical supercomputer. So there are different strategic applications of this quantum domains, and one which I discussed just now is that factoring large integers, and for simulation or this kind of engine analysis, whatever, what is the how we can optimize the battery design or something. So you can have an efficient design on simulation of those batteries on a quantum. And optimization, because this quantum computer can solve this optimization problem fast compared to classical machines. So whatever optimization problem you have in your life can be solved on a quantum computer. Maybe it is traffic optimization or traffic systems and these problems. Large database searches. So using robot search, we can do it. Something will take hundreds years on a classical computer, but will be seconds on a quantum computer. There are other applications also. And this is basically kind of simulation kind of thing only. So you can do a simulation of this drug's effect on or how to mimic the human brain or robotics. So these kind of things which are today also we simulate on classical machine, but we approximate number of parameters in there, or we do not go for precise thing. Yeah. Yes. That we will be having in the presentation later on, second session. How to encode the classical data into quantum states. Yeah. Yeah. Any questions so far?